All right, here's part two. We're going to start off by taking a look at some problems which now it would be reasonable to use a calculator, but not always necessary to use a calculator. And so we're going to take a look at this problem where they're giving us this expression x squared minus 9 to the 3/2 power. And they're telling us that x should be greater than 3. And so this statement right here, don't be thrown by the fact that they're putting in this expression that x should be greater than 3. Okay, this is just telling us that we don't want a negative number to show up in here, because remember the 2 on the in the fraction here is really saying square root, and we can't square root negative numbers. Like if you plugged in something smaller than 3, this expression is going to become negative number, and we don't want that to happen. So this is just what's called a domain restriction. Oops, excuse me. This is a domain restriction, and so this is basically saying we're just going to tell people don't put negative numbers inside of here, because that will be a problem. So don't be thrown by this. It's just kind of a part of the problem that's necessary, but for us really doesn't apply to answering the question. So what they're wondering in this problem is, what are some other ways that I could write x squared minus 9 to the 3/2? And they're giving us 4 choices, and they're saying any of these 4 choices might be valid, and your job is to figure out which ones work. So let's take a look at x squared minus 9. X squared minus 9, if you take a look at my choices, there's a bunch of x plus 3, x minus 3s. And that's because x squared minus 9 is actually a factorable expression. So I'm going to come down here and I'm going to rewrite x squared minus 9 and say this is really the same as, okay, x plus 3, okay, and x minus 3. Okay. And, right, so that's the x squared minus 9. There were parentheses around x minus 9, so I'm going to put big parentheses around this, right? That's these big ones. Okay, and now it's being raised to the 3/2 power. So all I did was I just simplified, or I factored x squared minus 9. So now we need to look at, okay, well, all of these problems are in radical form, so how do I get this to be in radical form? Well, remember, the denominator of my rational exponent means the same thing as the index of a radical. So I'm going to rewrite this now. Instead of writing 3/2, I'm going to take the denominator and I'm going to turn that into a radical. And remember, there's a little index of 2 out here because I have a denominator of 2. The inside of my radical, the radicand, is actually the same as the base of my exponent. So inside here, I'm going to put x minus 3 and x plus 3. Okay. And so now, I need to decide, what do I do with this numerator? This numerator 3 is just an exponent. I can place it wherever I want, right? So I need to decide, do I want to put it on the outside here, or do I want to put it on the inside here, right, and figure out how to use it. All right, so let's consider both of our possibilities. So the first thing we're going to do, let's kind of just pause, and let's look at our choices, right? So the first thing I'm doing is I'm looking at my choices, and I'm saying, hold on, this has an index of 2. Choice letter A has an index of 3. This is cube rooting, this is square rooting. So I can definitely say A is not a possibility. All right, so let's get rid of that one. Choice B, it has my exponent of 3, this, right? And it's kind of, but I have this big parentheses around x minus 3 and x plus 3, and it's saying let's raise the entire expression x plus 3 and x minus 3 to the 3rd power. Compare that to letter C. The only difference between these two is that this one has big parentheses around x plus 3 and x minus 3, and letter C doesn't, right? It's kind of just putting the 3 on the inside. And so we have to decide which one of these, B or C, is equivalent to our expression here. And if you notice, this one has big parentheses around x plus 3 and x minus 3 as well. And this exponent of 3 applies to the entire thing. When we look at choice letter C, this 3 only applies to the x minus 3 that's right before it. It doesn't apply to this x plus 3. And so we actually have to eliminate this choice because it's not giving the exponent of 3 to the entire expression like it needs to from our original expression. So I'm going to say in this case, choice letter B is good. This is a good example. This would be like saying, all right, I'm going to take my 3, my exponent, and I'm going to apply it on the inside right there. That's what we did. That's what choice letter B is saying. Okay. So now we got to look at this and saying, well, what's going on with letter D, right? This one's got this expression on the outside and this expression on the inside. And why is that? How could that be similar to what we have? Okay, so here's the kind of the way that we can go about this. If I take this expression x plus 3 and x minus 3, and I'm going to come off the side and you say, you know what? I'm going to take this value u, And I'm going to replace x plus 3x minus 3 with u. X plus 3x minus 3. I'm going to make these equal. And I'm going to go into my expression, and anywhere there's an x plus 3x minus 3, which is just once, I'm going to replace it with a u. I'm also going to not write my index of 2, because remember, this is just square rooting. Okay? So instead, I'm going to say, instead of x plus 3 and x minus 3, I'm going to put u. And that expression was being raised to the third power. So if I were to ask you to simplify the square root of u to the third, well, we'd say, well, that's made up of u squared, okay, and u, okay, and the square root of u squared is just u, but no longer under a radical, okay, times the square root of u, right? And this is something we've done. Very first thing we did with radicals was simplifying expressions that look like this. So if you notice, what happened was, and a u expression came out of the radical, and a u expression had to stay under the radical. But remember what we did at the beginning. We actually said that u was made up of x plus 3 and x minus 3. So now I'm going to replace u again. I'm going to say this u really means x plus 3 and x minus 3. Okay? Whoop. Let's fix that. X minus 3. And this radical also has a u under it. So I'm going to replace this u with x plus 3. And x minus 3, right? So just to make our lives easier, instead of having to look at this big expression, we just said, you know what? I'm going to make that expression equal to just a variable, which we're allowed to do. That's fine. Variables are there to be placeholders for expressions. And so I just made this complicated expression look simple so that now when I look at it, it's very easy to see that this simplifies. And then I can go back at the end and say, now that it's simplified and I've done all the hard algebra of getting it in its simplest form, I can replace it. And if you notice, after I put the x plus 3 and x minus 3 back into the expression, I have choice letter D. So I'm going to say D is also a good option. Okay, so this is the kind of the unsimplified version because I have more than 2 of these in the radical, and this would be the more simple version. But they're both equivalent to what I started with. Okay, so this is kind of a pretty detailed problem. So we're going to try another one, very similar, okay, and just see how this works. So we're going to go a little bit more quickly. So again, I'm going to take x squared plus 1, which is a factorable expression, and I'm going to turn it into x plus 1 and x minus 1, a difference of 2 squares. And I'm going to say that this expression, the whole thing, is being raised to the 5 over 2 power. Okay, and so remember, an exponent of, an index of 2 comes from a denominator of 2. So I'm going to turn this into the square root of, okay, x plus 1 and x minus 1. And then just for emphasis, I'm going to put that this 2 is the index out here. But remember, that just means square rooting. And now I got to decide what to do with my 5. Right? So I'm going to place the 5 around this whole expression on the inside. Remember, this was what was being raised to the 5 over 2, which means now it's being raised to the 5th power on the inside. So if you notice, that's choice A. That's a good option. Okay, I'm going to eliminate choice D because that's the option where they're forgetting that the whole thing needs to be raised to the 5th power and not just x minus 1. I'm also going to eliminate choice B because it's not an index of 5. It's supposed to be an index of 2. Okay, and now I'm going to again do a U substitution. I'm seeing 5 of this thing on the inside, and if I have an index of 2, that is far too many exponents, right? So I'm going to again do a U substitution, and I'm going to say U is equal to x plus 1 and x minus 1. Okay, which means anywhere that I saw an x plus 1, x minus 1 expression, I'm going to just put a U. So now this becomes the second root, not the third root, the second root of u to the 5th power. Okay, this expression went away and I replaced it with u. And again, we can see that this breaks up into the square root of, which again, I'm just getting rid of the index of 2. We don't need to write it. U to the 4th times u. Okay, so u to the 4th, when I square root u to the 4th, I get u squared times u. Okay, and now that I've had this simplified, I'm going to put back the more complicated version. Instead of u is really this expression. So I'm going to call this x plus 1 and x minus 1 squared, whole thing squared, times the square root of x plus 1 and x minus 1. Okay, and so now I'm going to look back and I'm going to say, this is close, right? I have this down here, I have the whole expression being squared, and here I have each of the parts being squared. But remember, we have this rule that says if you have 2 things that are being squared, it's the same thing as squaring each of the parts. And so I can actually take this 2 and give it to each of these separately instead of having it on the outside. So this is a good valid expression Right, so again, I have a couple of possibilities that both mean the same thing as x squared minus 1 to the 5 over 2. All right, let's move on and let's take a look at, it says rewrite the expression as one rational expression that is equivalent to the expression for all values where x is not equal to 1/2 and plus or minus 5/4. So again, there's some information here that's it's necessary, but that we don't really need to worry too much about, and that's this for all x values not equal to. This just means there's some domain restrictions and we need to let people know about them. Okay? So we're just kind of like, for our purposes, can ignore this. What they're really asking when they make this statement is to rewrite it as one rational expression is to subtract. These things can be put together and you need to subtract them. So I'm going to subtract by finding a common denominator. So I'm going to leave the numerators alone for a moment, and I'm going to factor each of these denominators. 16x squared minus 25 turns into 4x plus 5 and 4x minus 5. Okay? Because, remember, this is a perfect square, and so is 25. Okay? And my second expression, you can do your AC factoring. It's negative 40 and 6, and this one turns into 4x plus 5, okay, and 2x minus 1. Okay? So again, I'm not going to go through the process of how I got this expression. This is something you should know how to do. Pause the video if you need to, and off to the side, just do your AC factoring and show that this works. Right? So I'm looking at these denominators, and I'm noticing that the first denominator has a 4x plus 5 and a 4x minus 5, but it does not have this 2x minus 1. So I'm going to bring in a 2x minus 1. So I'm going to say the numerator is 3x minus 5. That was there already, right? My denominator was 4x plus 5 and 4x minus 5, but I'm claiming that we need a new 2x minus 1. So I'm going to bring in the 2x minus 1. Okay? And I need to do that in the numerator as well. It also needs the 2x minus 1. I can't change the denominator without also changing the numerator. And now I'm going to subtract. Okay? And again, the 4 was here. I had a 4x plus 5 here and a 2x minus 1 already. Okay, this was just the same problem. I just rewrote it. And I'm going to introduce a brand new. I'm looking at this one and saying, I see a 4x plus 5 and I see a 2x minus 1. But the one on the left here has a 4x minus 5. That's new. This is not showing up in the right, so I need to introduce that. 4x minus 5 needs to be over here, which means I need it in the denominator and the numerator. So now, denominators are the same. All three factors are showing up in both denominators, and that means that I can simplify the numerators. The first numerator is a FOIL problem, so we're going to say this is the same as, again, I'll let you do all the little stuff, 6x squared minus 13x plus 5 over my denominator, which again is just all three terms, which you do not need to, for the purposes of this problem anyway, actually multiply out. Just leave it factored. And my second one's just a distribute. 4 times 4x is 16x. Okay, and 4 times negative 5 is negative 20, right, over, again, this big denominator, which we're just going to leave unfactored, 4x plus 5. I'm just going to switch these so it matches. I'm going to turn this into a 4x minus 5. Okay, not necessary, but again, just to look nice. Okay, and now that my denominators match and everything's all factored out, I can just do my subtraction. I see 6x squared minus, I don't see any x squareds on the right, so I'm just going to bring that down, nothing to change it. Negative 13 minus 16, those are both x to the first, so I can subtract those, right? And so I'm going to say negative 13 minus 16 is negative 29x. And now this is the one we have to be careful about. This is 5 minus negative 20. So I'm going to come off this side and write that. 5 minus negative 20. That's like adding 20. This is really plus 25. And again, it's all over this big denominator, which I'm going to have to rewrite one more time. 4x plus 5, 4x minus 5, and 2x minus 1. Okay? And so I would say my one fraction, right? Okay, let's go back to the beginning. It's a rewrite it as one rational expression that is equivalent. Here's my one rational expression. I put together these two fractions. Now there is only one fraction, and so this would be the simplified rational expression. Right? So let's try one more of those, because there's a slightly different thing that happens here. So the wording's all the same. Again, we have our domain restrictions, which are necessary for the problem, but not necessary for us. We can just ignore those. And so I'm going to take this one and say, I'm going to take the x plus 5 and leave it alone. And I'm going to factor the denominator. And the denominator in this case, again, you're going to have to come off to the side and do some AC factoring to figure this out. Just for the sake of time, I'm just going to tell you that it's x plus 5. And it is 2x minus 5 as my factors. My second fraction, again, I'm going to leave the numerator alone, and I'm going to factor the denominator. This expression is AC factorable again, and it turns into 2x minus 5 and 3x plus 1. Okay? 3x plus 1. All right. So here's where this one becomes a little different. Okay? I'm looking at my factors, and I'm noticing that they both have a 2x minus 5. That's good. The second one's got a 3x plus 1, which is not showing up in the first one. And the first one seems to have an x plus 5, which we need to bring over here. But here's the interesting thing. The numerator of the first fraction also has an x plus 5. So I'm actually going to cancel those. I'm going to simplify the first fraction. And what that's going to do for us, I'm just going to put a 1 up here now, is it's going to make it so that now I actually don't need to bring that x plus 5 into the second fraction. It doesn't exist in the first one anymore. So watch where I'm at now. 1 over 2x minus 5, which I'm going to put this in parentheses. Okay? And the second one now looks like 3x over 2x minus 5 and 3x plus 1. Now when I do a comparison, I'm going to say that the first fraction still needs the 3x plus 1, which I'm going to introduce just right here. Okay? Numerator and denominator, 3x plus 1. Okay? But now that x plus 5 doesn't need to be brought over to this second fraction because we got rid of it. Right? We canceled it in this first fraction. And so I'm going to say this one doesn't need to be changed at all. The denominators match now, right? 3x plus 1, 3x plus 1, 2x minus 5, 2x minus 5. They are identical. So now here's where I'm at. I can just add across the numerators, right? Remember, 1 times, I can kind of get rid of this and say I don't really need 1 times a fraction. So it's going to look like this. And now I can add across the top and say this is 3x plus 1, 3x plus 3x is 6x, 1 plus nothing in this one at all. So I'm just going to say plus 1 over my denominator, 3x plus 1 over 2x minus 5. Okay? So in this case, our denominator is not near as complicated. Take a look at our first problem. We had 3 parts in this one because there was no way at this step right here where I looked at the factored versions, there was no way to cancel out anything. 3x minus 5 on the top doesn't match anything in the denominator. 4 doesn't match anything in the denominator. So I had to kind of have those 3 parts because there was no way of getting rid of any of those 3 parts. When I look at my second one, when I did my factoring, the x plus 5's canceled, and I ended up with a simpler expression and a much easier time, right? I got a simpler problem that has only 2 factors in the denominator and a much simpler numerator than I would have had before. So again, a slightly different strategy, but it gets us to the same place where now we have one rational expression that is the sum of the original 2.